All right, well, welcome back, everybody. Hope that you all had a little good break there. We're going to get started again, and my next guest is going to be Mr. Peter Reali. Let me do an introduction of him. Peter is a valuable asset to SCU. He's an SCU executive board member with SCU since early 2018. He's our leading research project manager and is constantly helping SCU to stay on the scientific course. That's much appreciated. We need that. It was because of SCU's interest in scientific treatment of the subject that helped Peter decide that he was going to join us. It's a privilege of mine to have Peter come on board. Peter has a BS and MSEE from the University of California, Berkeley. I mentioned that. He had a long career in Silicon Valley, has an electrical design engineer and manager of engineering projects. His specialty was in telecommunications and network information technologies. He has designed systems including mobile telephone and control systems, fiber optic ring networks like T1, T3, and SONET communication systems. Currently is retired, lucky man, and enjoys a photography as a member of the Boise Camera Club. He plays blues harmonica. That's exciting. And with the Boise Blues Society, and does research with the Scientific Coalition for UAP Studies. He's done major sections in the SCU's most recent report, a forensic analysis of Navy Carrier Strike Group 11's encounter with anomalous aerial vehicles. He's also been interested in this phenomena for many years and has read extensively, but not participated in any group investigations due to time constraints and with his career, and is often the often sensational and unscientific methods employed by most organizations. Anyway, today, Peter's going to be talking about his title is A Statistical Treatment of the Drake Equation with the implications for the understanding of the Fermi Paradox and some hypotheses about UAP technology. So without further ado, Peter, it is yours.
Okay, well, let me see. Let me see if I can share my screen. Anyhow, well, thank you, Rich. Let me say that I'm very heartened today that we have so many people here interested in applying science to this very strange phenomena, anomalous phenomena that hasn't been treated with much dignity or importance in the past. And the SCU is dedicated to applying science to trying to understand this phenomena. So thanks, and I'll get started here. And I'll share my screen. Just a minute here. All right. Okay, let me screen. Okay, let's go here. All right. Some little bit of difficulty here. Okay.
Go up to view full screen.
Peter, go to view and select. Go to view.
We got it. Thanks.
Can you see it? On the top of the menu, go to view.
I'm trying to see view.
It's on the left. It says File, Edit, View. Can you see that on the top left above the word Tools?
Give me a second here. I'm trying to close some of this other stuff.
Go to the far left. No, the far left where you see. Okay, that's good. That's good.
That's good. Okay.
Yeah. Yeah.
If you click on view,
it's blanking my screen a little bit here, so I want to go to just get there. Okay. All right. Okay. So today I'm going to talk about the a little different twist on implications of the Fermi paradox and what I call a statistical R equation, which is taking the famous equation, and because I'm modifying Frank Drake's equation, I don't want to put his name on it, and I think I'll get some interesting results from this, which kind of surprised me. I hope it brings some advances in what we understand. So Rich is first, I think people often encounter the Fermi paradox, but I think few people really explain what the paradox is. And so I'll just, maybe many people know, but some others may not. In fact, I didn't even until I really investigated it. Well, the Milky Way contains from 100 to 400 billion stars and at least 100 billion planets, according to current estimates. And it's huge. It's 105,700 light years and about close to 13.8 billion years old. And civilizations could be many thousands, millions, billion years in advance of us. And so it's easy to calculate that with a modest percent of the speed of light, which there are current theories about how to do this at sublight velocities, and even a thousandth of a percent or less at 0.01%, which is 1/10,000th to the speed of light, you could actually traverse the galaxy 1,300 times. And at a tenth of that, 130 times, you have a hypersonic missile, which at minimum speeds 3,700 miles an hour. You could do it 7 times. Now, I realize this is ridiculous because the universe has expanded, but it just points out that civilizations could have populated the galaxy many times. And so the paradox is, where are they? Rich Fermi is famous for having asked this. And so I'm going to, the question I'm asking is, we may not be thinking right about this. So I'm presenting a hypothesis, and a hypothesis based on the extraterrestrial hypothesis, which I think a lot of us adhere to, but it is a hypothesis, and there may be other explanations for the UAP reports, and I don't rule them out. And if something, and I'm quite happy with whatever comes out, but it just seems to me, from what I've learned, that that seems to be the most likely source of this. From these, we can deduce the statistical inferences based on a few actual occurrences. So it's kind of a reverse Bayesian type of statistics, where actually these are the what are called the a posteriori statistics, which are what I use is the number of reported sightings per year, and I'll go into that how I derive that. And now I use that to make predictions of where to search for the origins and extraterrestrial locations in the future. This is a scientific hypothesis, so it can be falsified. You can actually do tests of this. And as time goes on and we get better telescopes, and that it'll turn out that the predictions I'm going to make at the end of the report will either come true or they'll be false, but at least it can be tested. And maybe if it's somewhat true, it'll lead to some more thoughts about what's going on. So this is based on 10 assumptions, a lot of assumptions. And if any of these are wrong, then of course, but I think they're reasonable anyhow. So the first assumption is if a civilization is advanced more than us technologically by what I call lambda years, and this could be 500,000, 2,000, they will become less interested in species, less advanced in themselves, and become hard to detect. This is conceptualized in what I call a time envelope, which I'll go into detail later. The second one is interstellar travel technology is going to be a natural result of advancements in science. People, this seems outrageous, but I go on the, I've read a lot of Ray Kurzweil, who's pretty famous in artificial intelligence, and he goes into, there's nothing to do with artificial intelligence, but he goes into how technology is advancing exponentially. And exponential growth is something that we're not familiar with. We think linearly, but exponential growth, the rate of change is changing exponentially. So it grows quickly. Third one is high intelligence seeks novelty over repetition. And it says it's a famous statement by Ralph Waldo Emerson, is that foolish consistency is the hobgoblin of little minds. So in high intelligence, which certainly advanced species traveling in the galaxy would certainly have. Fourth one is advanced technology and limitless resources of space will eventually solve all problems of scarcity for spacefaring species. So that there's often people make the claims that these visitors are coming here to get our water or steal gold or some other kind of thing. But I'm going to go into that a little bit and shoot it down as far as I'm concerned. The fifth one is that of all the parameters used in I call the R equation, but it's really derivation of the Drake equation. The most controversial is the lifetime, which I call the communicative lifetime of an average alien civilization. And I treat that statistically in my approach here. I'll go into that. And the sixth one is a communicative lifetime may not mean the civilization destroys itself or dies out, but moves on and becomes virtually undetectable. We don't know, this is my approach to dealing with it. And it is intertwined with another concept of the time envelope. Assumption 7 is like 1 to 5% of the number of reported UAP sightings are valid and related to the number of technological civilizations in a spatial volume, which I define as a detection sphere. And I'll talk about that later as well. This eighth one is a communicative lifetime of intelligent species is a result of multiple independent factors that can be modeled by probability distribution as a result of a famous theorem called the central limit theorem in mathematics and in statistics, which I'll also talk about that. The ninth one is I'll be using a lot of the derivations of Frank Drake and Claudio Marconi, who estimated the number of communicative technological civilizations via radio. I'm assuming if a civilization is trying to communicate via radio, it's also going to want to be interested in exploring space and the area around them. The 10th one is 2 scientific principles. The cosmological principle, which makes the supposition the universe is, as we see it, has laws and properties that persist throughout the galaxy and perhaps the entire universe. Although there are some current theories that challenge this a little bit, but they're still not accepted. And then the mediocrity principle, probably the most powerful principle assumption that I'm making in this whole report is that we are a typical example of an intelligent life-producing system in an average sense. And I'll show why that comes out that way. Now, I'll go in a little bit on the Drake equation. The Drake equation is basically a statistical estimate of the number of possible technical civilizations in the galaxy. It uses 7 independent fixed constants probabilities it's really 6 with the number of stars in the galaxy, and calculates, because they're all independent, you can multiply them together and get the probability of a species that would be willing to, become intelligent and spacefaring. The Marconi equation uses 7 parameters that are log-normally distributed, and so I'm using his figures for many of the parameters, which are pretty similar to the Drake figures, but have improved with knowledge since the early days. My modification is I take the 7th parameter, which is lifetime, which that lifetime was assumed that they disappear. I'm assuming that they don't. I'm not making that assumption anyhow, but that they become less interested in communicating. 2 of the constants I reduced by a factor of 10 because I thought maybe they were a little bit I wanted to be more conservative about it. And it derives a number of planets that would have technological technologies within 5 to 1,000 years of our own development. And this is kind of what it would look like. Okay, this is the Drake parameters. Go on. It's the current number of stars in the galaxy, a rate of star formation times the age of the galaxy. The next is a fraction of stars with planets. Then the fraction of planets that can potentially support life per star. The fraction of planets that could support life that actually develop life at some point. The fraction of planets with life that actually go on to develop intelligent life. And the fraction of civilizations that develop technology that releases detectable signs of their existence into space. And then the one I left out was the lifetime, which I make a probability distribution, multiply these together to get the number of planets that would be technological. And that comes out to about between 2.4 to 240 million planets in our galaxy, which is a whole lot of planets. Okay, I'll talk a little bit about probability distributions, just for some of you that may not know what they are, because the whole thing is based on this. Typically, any kind of random variable, and what's a random variable? Well, say you took 1,000 people and you measure their weight or how high they are. The central limit theorem says they will tend towards the bell-shaped curve. You probably were graded at some time in school on the curve. This is what they were talking about. Well, and how you use it is that once this has been through proper sampling and you get a good representation for the curve, you can take, say I have time as the basis, a lifetime of the civilization. If it's, you see, what is the probability that it might live 4 million years? Well, you go up here, you write over here, and you can read the probability is, say, somewhere between like 15%. And the same with 2 million years, same thing. Now, a second important one is the cumulative distribution. What it is, that's the area under this graph. And what you can do with that, and that's really important, and what I use, is in a certain segment, say between 4 and 2 million years, you can calculate how many civilizations would fall within that time range. And that comes with an important for my estimations of the time envelope of how long they'd be interested. The other, I have a lot of other distributions that are used in here because we really don't know how this is distributed. So I took a wide range of probable distributions and saw how they varied, and I'll talk about that. One, the important one that I settle on is the student t distribution, which is it has a tendency to, it's important because when you have very low sampling, and the whole accuracy of probability distributions are based on the good sampling. You get a wide range sampling of the random variable. It handles the case where the sampling is not so high. And in our case, all I have is observations of reported observations of UAPs over a 15-year period, and I'll talk about that. One other one is a triangular distribution, which once you determine in a certain period of time how many civilizations could probably be visiting us, and they also, their interest will fall off with time because I think it becomes less novel, that you can use the triangular distribution to determine that, and I did that. So I had to develop a model for the intelligent development of intelligent life. And excuse me, the estimated age of the universe is 13.8 billion years, and the current age of the Earth is 4.5 billion years. And the age of life is 4.28 billion years. Since all planetary formations rather unpleasant, I mean, you can imagine a molten planet, you know, it only took about 220 million years for life to start on Earth. And I think that's remarkable. For people to think there may not be life out there, I think that life wants to form, and I think we'll find it as our techniques for studying extraterrestrial planets and things, that we'll see lots of life. The author will use a figure of 4.6 billion years as a typical lifetime of technological intelligent life to evolve, and I call that epoch. And this is due to the mediocrity principle I talked about. I assume we are average. Every time we assume we're not average in the past, we were the center of everything. It's turned out to be wrong. And that's key to my approach here. Okay, given this current estimated age of the universe, this would allow for about 3 complete cycles or epochs of evolution to take place. And for assumption A6, communicative lifetime, they propose, what I did was okay, how long would this communicative lifetime last? It would have a mean of about 10,000. I assume 3 different possible lifetimes of 10,000 years, 1 million, and 100 million years, each separated by a factor of 100. Okay, and the model I invoke for this is a steady state formation and dissolution of technological civilizations, as depicted in the next figure. And I'm assuming an epoch of time is enough to reach some kind of stable average number of I call them CISs, communicating intelligent spacefaring species that exist in our current epoch. Okay, here's a model of it in a graphical form. The universe forms, and over this epoch, slowly life begins to take shape and more formed until it reaches kind of a steady state where civilizations are going into existence and civilizations are coming out of existence. And the probability just, we are here at this current period of time, in the third epoch. And what happens is and because of this steady state, the probability distribution remains fairly constant. Now, I'm assuming this is within a detection sphere, somewhere like 1,000 light years, maybe 10,000 light years or less, or something like that, and within a few hundred millions of years. Now, of course, as the universe expands, this thing will change going out. But for our particular case and what's happening in the, in the recent, in the cosmically recent time, this is a constant, and I base my calculations based on this. This is a diagram of what this might look like if you lay time out, and like here we are at current time. The Earth is here. The green area is what I call this time envelope, which is a period of time when we've started. We are a spacefaring civilization. We've gone to the moon. We've gone out, but there's some period of time where civilizations are near us or within some maybe 500 years or 1,000 years of us, but eventually I'm assuming they pass on and they lose interest and move on. They don't disappear, but the red area is they have gone on and are no longer actively exploring around like they do in the beginning. And so in this diagram, if we go, let's say we freeze time and we go out through space, that the average probability density of these things is fairly constant. The same is true if we freeze a certain period of space and we move out in time for several millions of years, the probability density would be the same. And we can see that, what does this show? It shows that the probability that a civilization would be near us in technology is really pretty small. This thing would be huge. There'd be millions of planets or stars that are involved in this. And I don't show, the blue area is when we were in the past, when we weren't capable of space. And all of these have a blue area, but it's just not shown, so the diagram just gets too complicated that way. But if you move up here, you would see that this particular civilization is still in the blue area. They may be doing these water wheels or steam engines or something like that. And there's a few that are in our area. And those are what I'm positing are possibly exploring. And I'll go into that further. Okay, why haven't radio astronomers detected alien transmissions? Well, the most sensitive radio telescopes that we have today are good at, will detect a non-directional signal out to about a light year. The closest star is about 4.3 light years, and unless a civilization knew about us and directed a concentrated beam of RF energy directly to us, we could not detect it. So would aliens know about us? So the Earth has been radiating electromagnetic signals for about 100 years, maybe you could say 120 years, early spark gap generators and early radio and Marconi and those kind of things. But radio really in 1920s, really, we've been transmitting stuff into space for 100 years that is probably barely detectable. This creates what I call the detection sphere. And in this example, it's a radius of 100 light years. It would be a sphere because radiation travels out in all directions and would be spherical. The detection sphere would contain about 720 stars, using the average star density that you can get. Astronomers have calculated this. We will investigate using statistical modification that we talked about of the detection sphere. We might have how many advanced technical civilizations we have within this detection sphere. Now, an advanced technical civilization may have better detection schemes. It could have some kind of quantum detection or some something that we haven't dreamed of yet, or beyond. But still, that doesn't enter into my anything I dealt with. But it doesn't mean they don't have it. Would a very advanced technical civilizations be interested in looking for other civilizations? Well, I get into that. This leads to the concept of time envelope, where alien civilizations may slowly lose interest in other civilizations for various reasons. Okay, what's the origins of a time envelope? Well, you can see from the previous diagram that we're not the only game in town. We may be in competition with many other planets. That's part of the mediocrity principle. There could be planets many behind us and many far ahead of us. And I think with some time, civilizations might be more interested in visiting more advanced species. But it would certainly, after 200 or 300 years of traveling around and looking at different things, you'd probably start losing interest. Search for novelty or more advanced species, I kind of covered that. Also, the abundance of resources, I mentioned this earlier, but I'm going to go into detail, removes the pressure of the requirement for expansion. Many people say they'd be expanding because they have to keep, getting resources for an ever-growing, population or whatever. And I just want to bring, I think my next slide talks about that. This is not a picture, but a representation of an asteroid in our asteroid belt. An asteroid belt is a series of basically leftover from either planetary formation when the sun was forming planets, and it's between Mars and Jupiter, and it has thousands, maybe millions of these asteroids. This is where a lot of meteorites come from. They get kicked out of their orbit and come to Earth. And this asteroid is called 16 Psyche. And it's made up entirely of nickel, metallic iron, and, with a solid gold core, and has diamonds in it. And I shouldn't say entirely, because there's many other precious metals in it. Its radius is about 70.215 miles and a mass of about 3 × 10⁻19 kilograms, which is a lot of mass. And its estimated value of the asteroid is close to $10,000 quadrillion in current U.S. dollars. The U.S. gross national product was $21.69 trillion in 2019. So Psyche represents 5 million years of the U.S. Yearly gross national product in value. Now, of course, this is exaggerated because most of the precious metals have value based on their rarity. And this would remove that. So gold might become worth like lead or something. But certainly it would have plenty of resources for us to use for any kind of expansion. And this is just one of them. There's many others that have different kinds of precious metals. And an alien civilization, this is common throughout the galaxy. All other, I'm sure that all of the solar systems, which were not unique, will have this kind of valuable property around them. And also, there's plenty of water out there you can make from ice, and so the idea that they're expanding based on that, I think, is spurious. Less advanced species may offer little interest to more advanced species as time goes by. I mean, I think that that's already happened for us. And 100 years ago, we were more interested in, there's still some interest, but in investigating less advanced tribes and things in the world. Now we've sort of moved to kind of protect them. The possibility of excessive biological incompatibility of life forms. The idea that life is going to be like us, I think is naive. I think that probably if you just look at life on Earth, most of it is quite different than we are. And so there may be biological incompatibility of life forms. I mean, it could be that they're horrendous to look at. They're maybe just shocking beyond anything we can understand. Or they may have viruses or parasites or things that make it, or the gases that they use to live on may not be compatible with us, you know. So that might be one reason. Less advanced species may be more dangerous. And I think, like, what if a UAP landed in North Korea? You know, probably would not be good for the North Koreans or for the advanced species, since we're still fairly primitive in how we deal with things, especially with differences. Less advanced species may suffer from harm to their natural development by contact with more advanced species. You see this in Star Trek. They have the prime directive, where they don't want to interfere with the development of a less advanced species because it destroys their cultures. And there have been examples of that on Earth with you know, less advanced cultures having their culture basically wiped out. By the same token, more advanced species may offer more interest, but become dangerous to encounter. It could be that the reverse process, that your culture is a spacefaring species, but it becomes very dangerous to come on to these very advanced species, which may destroy your culture. Okay, now I'm going to talk about, this diagram shows a representation of spherical volumes, both in space and time. It's a little bit hard to combine all these, but the detection sphere, the units are light years. It's a spatial sphere of volume, and the time envelope, its units are years. It's how far in advance a civilization is from us. And the detection sphere, yeah, I've gone through quite a few. There's no reason why the detection sphere and the time envelope should have the same dimension, should have the same size. Like, but it turns out in my calculations that it comes out for a nice match with our observed encounters, that having a detection sphere between 500 and 1,000 light years and a time envelope between 500 and 1,000 light years kind of comes out to where it matches. And that was why I chose those time periods. What happens here is that this region in here, I've shown it as green, is when their civilizations are still interested in exploring quite a bit. But as time goes on, they begin to lose interest and get involved in other things. What they are, I don't know, but you know, they're advancing, and this reaches a maximum existential lifetime that where the average, I talked about this, is I've assumed that these lifetimes, three different possibilities of 10,000 years, 1 million, and 100 million years. And that's, I'll go into that some more. This is a rather complicated diagram, but this is taking the detection sphere and crushing it down to a flatness, and then moving all of the planets that are moved beyond interest in wide exploration, and left just here's Earth here, and these are the ones within our time envelope. And this is a probability distribution, a hypothetical one, just kind of some, we don't know what it is, but I'm assuming it has some centrality. And we calculate, like I talked before, how many technological civilizations would be within this region. And those are candidates for exploring us. And I'll talk about that more. This one back here just shows that the probability in space of particular civilizations, how far in advance of us is random, and it'd be equal likely that they could be ahead of us or behind us. There's no relationship between spatial location and their degree of advancement compared to us. This is the triangular distribution, and I use this to determine with probability this interest I talked about within the time envelope. I just have these in indeterminate units. Within a time envelope, interest is very high in the beginning. Almost all of the planets probably have some interest. They're sending radio into space. They're traveling around and doing whatever they're doing. But you know, they could become. We could encounter them. But as time moves on, it slowly falls off to eventually. I just use a linear thing here to be simple. It falls off to near zero, when actually you could also assume like a exponential distribution where it never falls off but gets very, very small. But this is for simplicity. I took this. And in a non-symmetrical distribution, unlike say a symmetrical one, the important factor is what's called the median. It's not the average or the mean, it's the median. And what the median tells you is that in this region, if you move in this direction from the median, the probability that a group of exploratory species would be less, that they'd fall within this range. And if you move in this direction, it's also, it becomes less. So the median is like the most likely value that you would encounter with this. It's kind of like an average for this kind of and I use the median in my calculation. So if there was say 1,000 species that could possibly be visiting us, it's most likely, but they're within this, they're falling off in interest. It's more likely that about 300 of them we might encounter. Okay, now what's some of the implications of this? I propose that civilization advanced of us will eventually develop interstellar travel capabilities. Okay, technology sufficiently advanced beyond us may no longer look like machines or be recognizable by us. Like UAP machine-like technology will be within 500 to 1,000 years. This could be varied. Other people could try other values, but this I seem reasonable to me. The 500 to 1,000 years was chosen using the thought experiment of Leonardo da Vinci on a cell phone. You give Leonardo da Vinci a cell phone, he's probably going to think, well, there's a liquid in there, and there's gears that are making this move around and whatever. We wouldn't have a clue about solid state electronics, or, you know, there'd be no way that he could determine what it was. And I think perhaps some of the UAPs that we see that are nebulous, many are natural phenomena, but some of those could be very advanced technologies that don't even look like machines to us. Okay, interstellar travel capabilities will not be remarkable, but a consequence of routine advancements in science. People find this outrageous, but I think that with the exponential increase in technology, that this will become, I think we have existence proofs that this is capable, is a capability that's possible. And if you believe that these are actual, if you believe in the extraterrestrial hypothesis, it says this can be done. If it can be done, it will be done. And I jumped myself here, exponential rate, so that's what produces that. Why is it exponential? All you have to do is look at like the sample of the advances between 1800 and 1900 versus 19,000 and 2000, or just in the last 30 years. We have the internet now, which is essential for everything. 30 years ago, we didn't even use it. You know, you had to go look up books, go to a library or something, you know. It's easy to forget that. And that's a huge advancement. This changed everything. It implies we'll develop some form of interstellar capability in the next 5 to 1,000 years. It's kind of a reverse influence. Okay. I'm going to talk about the communicative lifetime. The civilizations move beyond the 500-year time envelope. They will eventually disappear from communicative interest completely due to different reasons. Well, they might become extinct, you know, due to calamity, some type, like external supernova or internal shocks like war. This is often proposed for why there's no, we don't encounter alien civilizations, which is usually by people who haven't really studied the subject, but it's called the Great Filter, and that civilizations don't last very long and they basically become extinct. I'm not an advocate of that, but that's one thought. They may retreat into purely intellectual pursuits and be totally self-absorbed, some kind of massive brain treatment or something, and spend all their time doing mathematics or something. They may move on to pursuits that we no longer understand, just as ants can't understand international trade relations. Ants that have a hard time understanding that. They may merge with machines. That transhumanists propose, being reductionists, that we will eventually reduce our brains, or the connectome, they call it, to digital data, and would be loaded in a computer and become conscious. And so they would be in some kind of gigantic computer, but perhaps just your whole planet would become a computer, and they'd just be in there enjoying themselves. They may become decadent and regress to pre-industrial levels. This happened in Rome. Rome was fairly advanced, and finally became decadent, and was taken over by more primitive tribes, and not for another 500 years, there wasn't much advancement at all, and kind of disappeared. Okay, it's highly unlikely that civilization, there's many others. I mean, you could come up with all kinds, but I propose these. It's highly unlikely that civilization would be near us in technological development due to the age and size of the galaxy. And I put this up again for that very reason. The green there is a tiny portion of the communicative lifetime and existential lifetime, and and very unlikely we would encounter these. Most will be either way behind us or ahead of us. So I talked about this. I explored these 3 existential lifetimes. I kind of get mixed up and mix up communicated with existential, and I apologize that. But and if you say an existential lifetime is 10,000 years, it doesn't mean, it means that its average is 10,000 years. It could be 40,000 years, or it could be 1,000 years. It falls into some kind of a probability distribution, and all these are treated that way. Using a detection sphere of a radius of 500 light years would contain about 2 million stars. So there's 2 million stars. It's a lot of stars. And out to 1,000 years, it's 17 million stars. This is our calculation based on the star density, which is well known. We investigate using statistical modifications, Drake equation, and I've talked about that. Okay, I'll put that there. Okay, here's what I call the R equation, so that I don't involve Drake in this, and he gets blamed if this is, it's my own, it's my own development. Okay, I can't go into detail on all of this, but I basically take the 7 constants, and I multiply them together, and then I use a probability distribution between 500 and 1,000 light years to calculate how many civilizations that are spacefaring would be within a detection sphere, and we might encounter them. And because we don't know what that probability distribution is, we assume it's some kind of centrally organized one, because it seems like all systems tend towards a central centrality, like according to the central limit theorem. I assumed a uniform, log uniform, normal, and student t distribution, which I kind of showed earlier. And I base these based on the 3 existential lifetimes of like I talked about. And then I derive the percent of these planets that will be within a time envelope of 500 to 1,000 year period. And okay, really a number of UAP sightings reported each year. So how do I know what the sightings are? Well, there's not a lot of, you get all kinds of stuff, but I took this book, let's see if I can get this in on camera here. That doesn't work very well. Anyhow, it's called the UFO Desk Reference by Cheryl and Linda Miller-Coster. Now, I don't think the problem, there's a lot of problems with this book, in that none of the quality of the observations was scrubbed very well, and that's not their fault. This is a very difficult process, and the SCU is going through a process of taking reported events and scrubbing them to get separate the reliable from the unreliable. And but what I found was reliable was the number of sightings. So it gives the number of sightings in the United States over a 15-year period. And I took the average, weighted average of, and I get about 9,811 sightings per year. And I had conversations with Robert Powell, and who is, he's been studying this. He's a colleague of mine, and he'd be talking after me, I guess, today. And he's a longtime UAP researcher, and just like Rich. And he's said that between 1% and 5% of the reported cases, or between 400 and 9,800 reliable reports per year, are reliable. Now, people might complain about this and say, well, that's only the United States. But I thought about this, and if an alien civilization came through to investigate Earth, they probably just wouldn't land in Los Angeles or something. They'd be traveling all over the world. And so, and plus, many of these sightings are duplications of the same, same device. So I think it probably represents the world as well. Some of the ones seen in the United States are probably also seen elsewhere and reported. Further, many of these are probably duplicate sightings. So what I did was just count this to take 20% of those, which because you could fiddle around with that a little bit, but that's what I did, which produces about 20 to 98 sightings per year that are valid and of an extraterrestrial origin. Okay, what I do is for civilizations with an existential lifetime of 10 to the 4th years and a time envelope of 1,000 years, and all the distributions, going through all of the distributions I calculated, I get from about 3 to 250 exploratory species that could be possibly visiting us. This is some graphs of these calculations here, and what I found was that for existential lifetimes of 1 million or 100 million years, it doesn't match at all. It's almost zero that would be visiting us, according to my assumptions. But for 10,000 years, we start to get a kind of a nice match we can see that. I want to move this up here. Okay, we can see that it may be hard. You probably can't read this very well, but we get between 3% and 30% of the people of the civilizations in the time envelope who could visit us, and that would be like 2 to 250 visits per year. And I'm assuming a Poisson distribution here. A Poisson distribution is a probability distribution that is good for traffic models, like I'm used to in the telephone industry. You can assume a certain average number of telephone calls will come into a network, and you can calculate and design the network so that on the average, it'll be able to handle all the calls. And same with like radioactive decay, it's very useful. So I'm assuming that if there's a number of these form like a traffic. These civilizations are traveling around and encounter Earth, and visit for a while and then leave. I think the interesting thing here, and maybe I'll point out, is that I'm assuming there's lots of these, and that accounts for the differences in the various description of these vehicles. I think there's many ways to travel in space, and there's been many technologies. And I think the idea that there's one entity or one consciousness or something like that, from my perspective, doesn't seem the right way to look at it. And there's many of them. And with the time envelope, their interest falls off and new ones come. And that accounts for the changes that occur over time. So it's an interesting concept. We'll see how it plays out over the time. And so I'm going to move on here. Okay, this diagram is a plot of the different probability distributions, and the green area is the time envelope. And on the bottom here is the detection sphere radius. So I go from 500 light years out to 1,000 light years. And this is the number of civilizations that would fall within this detection sphere. And this takes into account the time envelope, how many would fall in this. And I really looked at 6 different distributions, but these two really don't. This is all for 10,000. This is all for a lifetime of 10, existential lifetime of 10,000 years. I've dismissed the million and 100 million years because I just don't get anything that agrees with what our observations are. And so the T distribution falls right into the center, and I like that. If you take these distributions, to my mind, they grow too quickly. They appear much too they produce too many observations that fit what we see. And if you go in this direction, you have to go too far into space to get the. I think that's kind of this kind of moves to a minimum energy for a system. So minimum energy is always kind of a nice way to segregate things. Things tend towards minimum energies. And so I took the T distribution, which is the one with the least, it gives the model for the least amount of sampling, which certainly fits fits my model. It just doesn't have, we don't have a lot of sampling. This, now we come to kind of sum this up. We're starting to sum this up. And this curve is shows the number of stars. And what I produce is like for 500 light years, 750 light years, and 1,000 light years. The green is in our time envelope. That means they could be visiting us. The gray is the median that we might encounter. The blue is how many civilizations are behind us. And the red is how many are ahead of us in this, in this time envelope. So we start out at 500 light years. There's potentially 9 civilizations that might be willing to visit us or moving around, but likely only 3. There are 9 civilizations behind us. Water wheels, steam engines, 129 ahead of us. These are warp drives and wormholes, all that kind of stuff, but we're not likely to see them. And for a total of 146, 750 light years, we got like 97 potential with 28 possible visitors, 69 that are behind us, and 1,499 that are ahead of us, for a total of 1,666. For 1,000 light years, we have 545 advanced civilizations that are in our time envelope, 588 that are behind us, water wheels, steam engines, 8,224 that are ahead of us, probably not going to see them, a total of 9,358. And we're likely to encounter 160 of them from this group due to the median. This sort of summarizes again, but it shows down here for the million light year and 8 million and the 10 and 100 million light year, the probabilities are near 0. And for a normal distribution, you might get 20 per decade, or about 2 per year. Uniform distribution about 34 per year. Log uniform 248, and T distribution between 3 and 160 per year. So, these are my conclusions for this whole thing. Is I've estimated a number of alien civilizations that are within 500 to 1,000 light years of us that might detect us, that might be interested in us and perhaps visit us. So these are CIS, Communicated Intelligence Spacefaring Species. 500 to 1,000 years defines a spatial detection sphere for visiting civilizations. The number of civilizations that might visit us per year, based on an average communicative lifetime of 10 to the 8th years, 100 million years, is 0, 0. 10 to the 6th is 0. 10 to the 4th is between 2 and 248. for all distributions. But for yearly sightings that are most likely to be visiting us, in a rough estimate, we get between 3 and 160 sightings. And this, I found it remarkable with all this that that there's even, it's close at all. I mean, it's within the same, order of magnitude. I wasn't really expecting such closeness, and so that may be a coincidence, but I think it's worth investigating. It's a hypothesis, and it's going to be scientifically tested as we move on. If we assume that UAPs are RCISs, then they have an existential lifetime of about 10,000 years, meaning that we kind of get an idea how long they would be around in some sense. The existential lifetime is, even though they're not visiting us, if you had a spaceship, you could go out and encounter them. They would be there, but doing something else. All other civilizations are either too advanced to be interested or unrecognizable or not far enough advanced to be able to detect this. So finally, so this leads to some predictions from the hypothesis I have. These can be tested, and maybe not today, but in the years to come. Everyone will probably forget this, but as long as I'm around, I'll be looking to see if they meet any of these, any of my predictions. And the probability distributions are very wide in variance and may not fit a normal type distribution. So probably a lot of the causes are not independent, but they are probably centrally organized. I mean, it's some kind of something like a t-distribution, or it's not just flat. Non-biological life should be very prevalent in the universe, and we should see detection of life forms when new telescopes like the James Webb come online in the next few years, or perhaps on Mars or other moons of the solar system. The reason I say this is that if technological life is so prevalent, non-technological life is going to be even more prevalent. And so we should be able, I think we've actually already detected life on Mars, or at least it was on Mars. I think like the Viking probe, and I think that the current detection of methane that seems to come and go, are signs that probably, and there's also been meteorites that scientists, are still debating, had signs of, this is a meteorite from Mars. They know by its composition, it came from Mars. And it has signs of microbial life in the actual meteorite. I think when atmospheres can be detected, we should start seeing presence of technological species within 500 to 1,000 light years of Earth. When extrasolar planets can be directly imaged, we should see faint technosignatures in the range of tens to low hundreds of planets within a 500 to 1,000 light year distance from Earth. All other civilizations are either too advanced to be interested in us, or unrecognizable, and not far enough advanced to be able to detect us. Further, Earth should develop, because of mediocrity principle, should develop interstellar travel within the next 100 to 1,000 years, and perhaps less than 100 years. Also, the existential lifetime of most advanced civilizations will average on about 10,000 years before moving on. So that concludes my presentation, and I guess we'll be open to questions.
All right, Peter, thank you very much. Go ahead and stop. You already stopped sharing. Oh, that's good. So let's go and start the questions that we've got. And I encourage people to go over in Whova and use the ask a question box over next to that window. Peter, you include 10 different assumptions. How sensitive to these assumptions is your analysis? If anyone is invalid, then what does that do? And assuming some validity for all 10, how sensitive is the math to variations in each assumption?
It's some are very, like the mediocrity principle is very important. If we're not mediocre, if we're special, we may be alone in the universe. I mean, it's that sensitive. Some of them are not so sensitive. It's a little hard for me to know which ones are, as sensitive. So I only think time will tell, and, how this works out. I think many assumptions like the central limit theorem is important. I'll just say that, it's a little hard to determine right now. And we need some measurements. We need to actually have some data.
All right. The next question, it says P3 Orions use MAD, magnetic anomaly detection. Is there anything there to discuss?
I had a hard time. Can you say that again?
I'm not sure that this is related, but anyway, it says P3 Orion's use of magnetic anomaly detection. Is there anything there to discuss?
I'm not familiar with that,
Yeah.
what's being referred to.
Okay. I'm going to go with the next question here. Have there been any calculations on the probability of civilization's development of interstellar nanoprobes and the deployment of nanoscale technologies as being more likely than a civilization's use of larger probes?
Well, that's very specific. Mine's a very general kind of analysis. I think that I've assumed that advancement, if nanoprobes are possible, I'm assuming with exponential type of advancement that this would become available, and it would become one of their technologies. Look at us today, and look at 100 years ago. If you showed somebody a cell phone, they'd know it was artificial, but they'd be dumbfounded at its capability. When I was a kid, Dick Tracy had a wristwatch that had like a television in it or something, and that was wow. Now it's just taken for granted. That we have cell phones and we can talk. This when I went to grad school, when I was in grad school in communications, cellular technology was still a research project, and yet here we are. At this time we can talk. We can have this conference, which is amazing. Video conference with people all over the world, and it works pretty darn well. So I can't address a particular technology. No.
Sure. The assumption of statistical independence between the terms, allowing multiplication of individual probabilities, is troubling. Has this been addressed?
Well, I think I said that it's probably not. I think towards the end I said that some of these, it's probably not a normal distribution. When I use the normal distribution, I get very low agreement with observed UAP phenomena. So it has to spread out. So it's probably that happens when some of the terms are probably not independent. And you can kind of I don't know all the factors to development and lifetime of civilizations, but probably not all of them are independent. Probably depends on where they're located and in the universe. But I'm assuming a detection sphere that's fairly near, close to us, 1,000 light years close on a cosmic scale. But I mean, it's phenomenally far for us. But still, it's probably going to be similar, But we don't know all the factors that affect the development of our intelligent life. But a lot of them are independent. But whether they all are is probably not.
Okay, Peter, the next question. Why not take into account the possibility of cooperation between civilizations? Why is everybody doing their thing all by themselves in these scenarios when symbiosis seems to be the way nature likes to organize itself?
Well, I don't know if I'm, I don't know what to, they may be cooperating. There could be some kind of a galactic council or something, and they're all cooperating. I'm not ruling that out. I'm just,
Sure.
Making the least amount of assumptions. I don't mean that there aren't some that are working together. Some may be incompatible. Just look at the problems we have with differences here on Earth. And it may not be uncommon. If we're average, then probably, it's probably our type of thinking may not be so uncommon. So.
There was a question is why isn't the possibility of faster than light travel added to any of these equations? You'd expect them to change everything.
Oh, I didn't rule out. They could get here instantaneously, but how fast they get here doesn't matter. Isn't it part of my analysis?
Sure. I'm
just estimating how many would be interested in coming here, and whether it's dangerous for them to come here, or we're dangerous. I know one encounter where so it was on a hunting expedition and people wanted to shoot at it. It's ridiculous. People are, because something's different and they're afraid, they get violent. And we have to get over that.
In your horizontal bar chart that you showed, where you had the distinct colors, it looks like they might have been epochs or something like that.
Yeah.
And you were showing. So somebody was asking, can you define what those colors were again? Because they didn't.
The green area is the time envelope. And what that is, that's a period of time when a civilization is close to us and maybe no more than 500 to 1,000 years ahead of us. They are interested in that period of time. They start out very interested in investigating, civilizations around them. As time goes on, 100 years, 200 years, 300 years, they get less interested and maybe are interested in other things, and the interest falls off. And that accounts for why we don't. This is a basis in my thought pattern of why we don't see millions of, species out there doing all kinds of things. And also, as technology advances, it may become much less detectable. That's sort of the take I take on it. The red area is they moved beyond, that's the existential lifetime. The green and the red and the blue are the existential lifetime. That is, they are still in existence. You could fly, if you had a spaceship, you could fly out and maybe see them, but they're not, the blue area, they're not really interested too much in exploring anymore. They have their own interests and are doing things we may not understand. And beyond that, I don't know. When you get beyond the red area, it's unknown. I don't think civilizations, I don't think intelligent life disappears quickly. I think intelligence wants to live and explore and grow. And that's kind of my period. I think here on Earth, at some times, the human race back, during the Ice Age and stuff, some of the tribes were probably down to a few hundred members, but they still survived an Ice Age. I don't know how we'd survive an Ice Age, with all our technology, but some would. And I think that advanced technology will, want to do the same thing and move on, and things will become more interesting, with that. So.
There's a question here that's you have mentioned databases from like MUFON and the other ones that, like, for example, Cheryl put together. And by the way, in case you didn't know it, I wrote the foreword to that book you're talking about.
Yeah. I sorry, I should have mentioned it.
Yeah. So anyway, you've mentioned databases from MUFON. I had once contacted MUFON for an ArcGIS project to show spatial distribution of the UFOs across the USA base on their characteristics. However, I was told by MUFON that they do not provide the accurate geolocations for safety reasons. Hence, I could not work on that project. Do you know of any credible databases that might contain true details for data analysis?
Rich, you might be able to answer that better than I do, since you and Robert were, high up in MUFON, and I wasn't.
So, typically when an investigator goes out, they put a precise, in their report, they put precise information in terms of location. And that report that they give is giving you more details. But the problem is that to the general public, what they did is they displayed it in a tool that basically didn't give you the precise location to the general public. So investigators, if you read the investigators report, you'd see that they had the locations down, but that data doesn't get passed or out to the general public to see. And I think you can understand why that they don't give precise locations. You don't want people coming out to your farm, wanting to see UFOs. Okay, so it's like they have to do a little bit of a change. But as far as databases are concerned, they may be in the database, but it's not what the general public might be aware of. And that's all I'll say.
I think they did a credible for what they had to work with. I think they did a credible job of. There's some interesting stuff here because it gives it per year. It gives it by state.
Yes.
It gives it by season, time of day. Yep. I think those are probably accurate. And so it does show some patterns. There's some patterns in here. And but I used it mainly for the number
Sure.
of reported events because I didn't know where else to get it. So
and one of the challenges we have with any of the sighting databases are that, and this is the same problem that the Air Force experienced, there are actually more sightings that are unreported than there are reported. And so if you're only looking at a population of reported, it's likely a very small percentage of the population out of the total sightings, if you would, that because the most people that I talk with over my history and stuff like that don't even want to talk about it, or they'll not bring it up. They won't even raise their hand if you ask a question like, how many of you have seen something? So anyway, statistics, that's the challenges we have.
The way I approach the possible large number is I think many of these are duplicates, that if a thing's traveling around, many people are reporting and have not reported the same object. So
Right.
This is a very difficult, actually, a good database on sightings would be, it's a phenomenally huge undertaking, but probably one of the most important things we could do would be to have an accurate understanding. But it's just a huge project to take on,
It is. And let me just say, I'm going to echo what you just said, because like in 2012, I followed a balloon that was launched here from NASA in Huntsville. And it was a Google Loon balloon. It was one of their projects for bringing internet to rural areas. And the balloon took off, and I had suddenly like 4 reports in the local Huntsville area that were coming in. And then because it was cylindrical in nature, it was easy to track on the MUFON database from state to state. And over the next 4 days, there were 40 reports of that same object traversing across multiple states, right? So you're precisely right in the sense that you could have that same object that's going across multiple states or seeing multiple times. And so that doesn't let you know how many objects are in the air. It lets you know that there's a whole bunch of people that might have seen the same object, right? So there you go.
That's why I discounted it,
Yeah.
the 20%,
No, I hear you. What is the source of the assumptions of the loss of interest and curiosity? Assuming that there are more civilizations going through the process, then there are always new civilizations to discover. Would there be a point of saturation of information? What of anomalies?
Well, that's probably one of the biggest questions that people might challenge me on. But I think that if you look at in the early 19th century, there was a lot of interest in science and going to like New Guinea and different places and investigating, these tribes that were living there. And as time went on, it started to interfere with, we destroyed many of these tribes by introducing, they have a culture, they have a process of developing. And today we tend to isolate them, and many of the, we tend to let them just develop on their own and try not to interfere too much. That's one aspect. The other one is you do something for 100 years, then you do it for 200 years. If things are sort of similar, if there's a lot of similarity, after 200 or 300 years, you probably get an idea how of civilizations develop, and there might be a few surprises out there, but your main interest would probably not be so much on investigating another civilization. You'd probably have other activities that you'd be, and it would only be intermittent whether you interacted with other in an investigative mode, to come. Just generally because of the mediocrity principle, I think we're mediocre. We're not that interesting. There's civilizations behind us, there's civilizations ahead of us, and so we're in competition with a whole. For us to visit us, we're in competition with a lot of other civilizations, and that's is why it falls off in time. That's my assumption.
Peter, do you have any desire or a plan to publish your work by any chance?
Yeah, this is kind of a work in progress. It's kind of, I started a white paper and then I got busy on the Nimitz report, which we worked on for about 1.5 years. And then I got busy on something else, and I've been intermittently working on this, and it has developed over time. And I will eventually produce a white paper that gets peer reviewed. This has not been peer reviewed. I've actually sent it out to some people, but peer review is tough. It takes a lot of time to peer review stuff, and it ought to be, I ought to have my act together, before I put it out. And it's still, I have more ideas on developing it and stuff. So I will eventually produce a paper and publish it probably within the SCU. Trying to publish this stuff in more regular journals. They just generally don't want to hear about, they still don't want, in spite of what everybody says, they don't want to hear about, UAPs or anything like that. They don't consider it, worthy, of being published.
Based on your analysis, do you think that universal life is an exception or a rule?
Well, I think I said in the end, I think it's going to be everywhere. I mean, it only took 220 million years. I mean, that's a lot of time to us, but it's been, the Earth has been around for 4.6 billion years. And early Earth was horrible. I mean, volcanoes and molten lava and, no atmosphere or toxic atmosphere, life formed. And in spite of all that, it wants to form, in my opinion. And so I think it'll be basically everywhere. Not every planet and everything, but I think it's going to be real common.
Here's a question. Have you incorporated the possibility that some civilizations have decided to internalize themselves and stay on their planet, living inside a simulation of their own creation?
Yes, I think the sixth term in the Drake equation is civilizations that are intelligent civilizations, but it's a larger number. But then when you get to technological civilizations, it's some fraction of those. So there would be civilizations that would probably not be interested in, I don't know if they'll call them a civilization, but there might be intelligent life that, is not so much interested in expanding beyond their environment, yet being intelligent. I don't know much more than that,
Sure.
What that would be like.
Question I'm going to read here is Contra Kurzweil. What is your opinion of the idea that the happenstance of fossil fuel wealth present on Earth created potentially unusual circumstances that spurred exponential technology development during the 20th century? How can we adjust for the potentiality that humanity's circumstances in terms of an available energy savings might be an aberration more than the norm in the universe?
I think if I understand the question, you're saying that the technology, it's mainly due to advancements in technology, mainly due to plentiful energy source.
Yeah,
it's an interesting idea. I think that I haven't really thought about that, but I think that again, the mediocrity principles that would I think that our Earth, there's probably lots of Earths like us or the equivalent. There's lots of energy sources, methane and, there'll probably be lots of gases and other sources of energy. At the bottom of the ocean, there's, creatures that live off volcanoes. They're not, they don't use the sun at all. They use the energy of the volcanoes. I don't know if that answers it, but that's an interesting proposition that, but I think that we're typical. That's my, in one form or another, on an average sense. So I don't think that would be a limit to technology.
There's a question here. Let me see if I can get this. How novas and supernovas happening in the different time envelopes would affect some terms of the equation if they wipe off some proto-civilizations still not capable to fly away?
Yeah, I mean, I'm assuming this is something like a bell-shaped curve, and out at the skirts on the left side would be civilizations that don't live very long, because unfortunately they, hopefully we're not there. There isn't a star nearby that goes nova or something, but we'd be wiped out probably. But it could be that they, they didn't get, they didn't get a chance to escape. They didn't. They didn't have space travel enough that they could get away and find a place to get away from the nova, and became extinct. I mean, they're not all 10,000 years. That's an average. So some might go 40,000 years and some might be 1,000 years, so that's kind of taken into account in the probability distribution.
One of the main problems that arise from databases where an investigator actually makes contact with a witness is limited to that particular investigator's experience. Would you agree that many good cases are passed over due to experience level?
Yes, but again, it's not to blame anybody. It's difficult to. It takes a lot of time, investment. These people don't get paid. They're volunteers, and our whole organization is a volunteer organization. It's very, people have lives, and it's difficult to, for them to be trained well enough and to get it, to get enough people to investigate all these things. It's difficult, and so I know there was one case that turned out to be not a UAP, but one of the persons said it was lens flare that people were seeing over the ocean, and that turned out not to be. That's what that person could do. Came up with the idea of lens flare, but when you saw the video, it was obvious not lens flare. So they make mistakes. They're humans, and so some of these are a result of that.
And this might be about the last question. Can we reach the conclusion based on your analysis that we as a species aren't really that interesting per se? But yes, anywhere, go ahead.
Yes, I mean, we always think we're so interesting, I mean, maybe we are, I don't know, but I think that we're going to be average. Every time, in the Middle Ages, they thought the Earth was the center of the universe, and there was a dome in the sky, and then it came like, the Earth was, and then they found out, that the Earth went around the sun, and that shook everybody up. And, they wanted to, Galileo, they wanted to, Copernicus, I think, Galileo, I can't remember which one. They wanted to torture him, for this, and on and on and on, that every time we think we're special, it's wrong, and so I'm just extrapolating that. I don't think we'll turn out to be special, in the long run.
Well, thank you, Peter. We've come to the conclusion of this session. We're scheduled at 2:50 to start the next one, so it's 2:49 according to my clock. But anyway, thank you so much for your time, and I appreciate everything that you've done for us in SCU, as well as your great presentations. So thank you.
Thank you, Rich, for putting this all together. I mean, I know the hard work you've done. It's, So thank you.
I'm going to be in recovery mode for many, many weeks to come. So, anyway, you all take care. Thank you so much. And we'll go to the next session now.
All right.